This is Atlas Launch Control at T-minus 2 hours and holding. We're in a planned built-in hold at this time on the launch of the JUNO spacecraft aboard an Atlas V rocket. We are now 2 hours, 32 minutes, 32 seconds away from the liftoff of the Atlas V. Liftoff is from Launch Complex 41 at Cape Canaveral. The JUNO spacecraft will provide the most detailed observations to date of Jupiter, the solar system's largest planet. Additionally, as Jupiter was the most likely the first planet to form, JUNO's findings will shed light on the history and evolution of the entire solar system. The launch window today extends from 11:34 a.m. to 12:43 p.m., a duration of 69 minutes. Following the 5-year cruise to Jupiter, which will include a gravity assist Earth flyby, JUNO will enter into a polar orbit around the planet, completing 33 orbits during its science phase, before being commanded to enter Jupiter's atmosphere to complete the mission. JUNO will orbit the planet every 11 days, coming as close as 3,100 miles to Jupiter's cloud tops, while measuring magnetic and gravity fields, atmospheric composition, and performing infrared, ultraviolet, and visible light photography. The JUNO spacecraft is unique in several ways. It's the first solar-powered spacecraft to perform operations this far from the Sun. To accomplish this, JUNO is equipped with 3 very large solar arrays, which, when extended, bring the spacecraft to a total diameter of 66 feet. To combat its exposure to radiation during its year-long orbit of Jupiter, most of JUNO's electronics have been housed inside a titanium vault in the center of the spacecraft. JUNO will be spin-stabilized throughout its mission in order to maximize the scientific observations. We've had a weather forecast from our launch weather officer, Clay Flynn, and the forecast is essentially unchanged from what we've been watching all week. There is just a 30% chance of not meeting the launch weather criteria. There will be a chance for some isolated showers. Winds will be out of the southeast at around 12 knots, visibility of 7 to 10 miles. Winds generally from the southeast, and a temperature of approximately 86 degrees. We've got some video now that was taken yesterday of the rollout of the Atlas V to the launch pad, which began at about 8:01 a.m. in the morning and took about a half an hour to complete. There is the entire Atlas V in the vertical integration facility at Launch Complex 41. That's a time-lapsed picture of the Atlas V headed out to the pad. This is one of the larger Atlas fairings, 16.5 feet in diameter. And the entire rocket, as we see it there, is just under 200 feet. It's 197 feet tall. The fairing covers the JUNO spacecraft as well as the Centaur upper stage. The Centaur will provide the final kick to get JUNO en route to the planet Jupiter. The entire flight today will last just under 54 minutes when it will separate from the Atlas V. And about 5 minutes later, we will have acquisition through the Deep Space Network Canberra station, and we will have some data from Canberra indicating the solar arrays are beginning to deploy. SDO atop the Atlas V weighs 6,555 pounds. And we're back now with a live shot at Complex 41 of our Atlas V rocket. At T-minus 2 hours and holding, this is Atlas Launch Control. This is Atlas Launch Control, T-minus 2 hours and holding. This puts us 2 hours, 19 minutes, 20 seconds away from a liftoff at 11:34 this morning. We're not working any technical issues, but we'll have confirmation of that very shortly. Our NASA Launch Director, Omar Baez, will be polling his team in just a minute. Now, we should be able to hear that. And he will report that to our United Launch Alliance Launch Director. And that will kick off the steps to begin our preparations for the cryogenic loading of the Atlas and the Centaur. And once again, no change in our weather forecast. Still just a 30% chance of an isolated rain shower. And our first activity will be the start of the tanking for the Centaur stage for the liquid oxygen, and that will be followed by starting the tanking of the liquid oxygen.
Voice check on 1.
On the Atlas.
I read loud and clear on 1.
At T-minus 2 hours and holding, this is Atlas Launch Control.
Test 1.
Conditions for today's JUNO launch is there are no COLAs. The LWO's forecast only shows a 30% probability of violation, and his concerns mostly with cumulus clouds rolling in around the noon time. And the range and the vehicle are working no issues. With that, I'd like to poll their team for readiness to proceed with cryo tanking. NASA CE.
NASA CE, go.
Go, I copy. ACE. NASA MEM.
NASA MEM is go.
SMD.
SMD is go.
SMA.
SMA is go.
NAM.
NASA advisory team is ready.
Copy that. The NASA team's ready to proceed with cryo tanking.
A voice check on 1.
Loud and clear.
Pre-test briefing. This operation is classified hazardous. Cryogenics will be loaded into the Atlas and Centaur stages. Ordnance items are installed and high pressure and inert gases are in use. Any anomalies will be brought to the attention of the launch conductor. Evaluation will be performed by a support team led by the anomaly chief and the vehicle system engineer on channel 6. COM channel 1 will be the primary command channel, with backup being COM channel 2. The following documentation will be in use for today's operation. OTP X45-LC029-SLC, revision 0, run 2. Deviations, there is one, R001, has been approved and integrated with the procedure. PSM document configuration, AV029, revision Foxtrot. Readiness poll for cryogenic tanking. Atlas systems, propulsion.
Ready.
Hydraulics.
Ready.
Pneumatics.
Ready.
LO2.
Ready.
Water.
Ready.
Centaur systems, propulsion.
Ready.
Pneumatics.
Ready.
LO2.
Ready.
LH2.
Ready.
Has gas.
Ready.
Electrical systems, airborne.
Ready.
Ground.
Ready.
Facility.
Ready.
RFFTS.
Ready.
Flight control.
Ready.
Instrumentation.
Ready.
COM.
Ready.
GCQ.
Ready.
Umbilicals.
Ready.
ECS.
Ready.
Redline monitor.
Ready.
Quality.
Ready.
OSM.
Ready.
ULA safety officer.
Ready.
Range and weather.
Ready.
Launch director.
Launch director is ready.
Proceeding with the count. Verify count to start at 13:24 Zulu.
Roger. Count will start at 13:24 Zulu. On my mark, time will be T-minus 2. Counting.
Coming out of the hold now in 3,
3,
2, 1.
Mark.
T-minus 2 hours and counting. We have one remaining hold in this countdown, a 10-minute hold. So that brings us to being about 2 hours, 9 minutes, 50 seconds away from launch.
Flight level.
Roger.
Pressurized Atlas RP1 tank to step 2.
Roger.
Adjust the ISA temperature to 110 degrees F.
Roger.
Apply onboard video power.
Roger.
T-minus 1 hour, 59 minutes.
Initiate CEC safing purge.
Roger.
Start CEP to high flow.
Roger.
Start CFA purge in displacement mode.
Roger.
This is Atlas Launch Control, T-minus 1 hour, 57 minutes, 54 seconds, and counting. Joining us now here in the Atlas Space Operations Center is Jan Chotis. She is the project manager for the JUNO spacecraft from the Jet Propulsion Laboratory. Jan, would like to welcome you. We're glad you're here, and I know you've looked forward to this day for quite a while, and it's stayed on schedule, hasn't it?
Thank you, George. Yes, it's very exciting to be here today.
The project really began about how long ago?
Well, the early ideas for JUNO came as long ago as the late 1990s. JUNO, the proposal started around the 2003 timeframe.
And from the time that we actually began to work on building a spacecraft until now has been about how long?
We really started the implementation phase of JUNO in September 2008, so it's been almost 3 years to do the detailed design, the development, build, and test of JUNO.
Well, let's look now at some of the activities that have been going on here at the Cape at the Astrotech Space Operations Facility near Kennedy Space Center to get JUNO ready to fly. So if we can go ahead and roll that tape, and Jan, tell us what we're seeing.
This is the day that the JUNO spacecraft was transported from Lockheed Martin, Denver, to the KSC facility. Here's the C-17 coming in on the shuttle landing strip. It's carrying the main spacecraft bus portion of JUNO. You can see it in this box here. The high gain antenna was also on this flight in a separate box. The solar arrays, the 3 large solar arrays, had been transported by truck earlier. The C-17 crew was from Charleston. They gave us a superb ride, the smoothest ride, much smoother than the rocket will be. Here you see the ramps at the back of the C-17 folding down in preparation for offloading the 2 big boxes. This is the one containing the spacecraft bus being slowly rolled down out of the C-17 onto the tarmac. We landed at about 7:45 p.m., and so by this time it was quite dark. This is the truck that transported the spacecraft bus over to Astrotech. A similar truck carried the high gain antenna in its slightly smaller box. We arrived at Astrotech around 2 a.m. and we waited until the next morning before picking the box up off the truck with a forklift and then putting it into the truck lock here at the Astrotech Building 1 facility. We closed the door on the truck lock and then proceeded with the unpacking of the spacecraft before moving it into the clean room. So here you see the spacecraft bus being unpacked. We double bagged it for extra contamination controls. And you can on the sides you can see the solar array simulators. Those are not the flight solar arrays that we carried on that flight. The bus was taken into the Astrotech clean room. It's on the rotation fixture now in the background, and the rotation fixture is over on its side, which is a position that we used to access and work on the spacecraft most of the time. In this view, you can see the high gain antenna being attached to the struts that are on top of the vault, which is all on top of the spacecraft core bus. When we do a hazardous operation such as this, we're always careful with QA and safety. I mentioned that the solar arrays had come down by truck a couple weeks before the spacecraft arrived. We deployed each of the arrays, tested the solar cells, and here you see some of the blanketing going on the mag boom, which is on the end of wing 1. The blankets are used both for thermal reasons and also for micrometeoroid protection. We have 264 blankets on the JUNO spacecraft. It's really a phenomenal blanketing job. Took a lot of detailed work. Now we're putting wing 1 onto the spacecraft for the final time. You can see wing 2 there in its stowed configuration in the background, and here's wing 1 flying in carefully towards the main bus. And they're just going to be attaching it onto the forward deck and the toggle link assembly. We deployed each of the arrays once they were installed on the spacecraft with the firing of test separation nuts. Here you see a container that they're taping on to catch the separation nut as it flies out. So that's exactly what's going to happen 5 minutes after separation. We're going to fire the top pair of separation nuts, and then we're going to fire the bottom pair, and the arrays will start to deploy. On Earth, we cannot have the solar arrays deploy as they will in space, so there's a very carefully constructed support equipment, a set of fixtures that support the wings, and we just walk them out manually. We follow that up with a test of the solar cells to make sure that the strings that make up each circuit are connected properly and providing the connection into the power bus. Here's a view of the JUNO spacecraft with all wings stowed. They've all been tested successfully, and we're trying to move to our next step, which is detaching it from the rotation fixture and moving it over onto a transporter to go over for fueling. Here is a picture of the spacecraft during its wet spin test. It's already been fueled. You can see the beautiful MWR antennas and the instruments as it rotates. This wet spin test was done to verify our mass model for all the parameters that we use in our flight software. Models matched up very well. Finally, we placed the spacecraft on the payload adapter and closed the payload fairing around both sides. So you can see the two fairing halves coming close together. JUNO is not so tall to fill the top side of the fairing, but it needed the 5-meter fairing for the width. So here we are completing the close-up of the fairing activity, and they've removed the fairing support fixtures. So now you can see the nitrogen backfill pipe there, and on this view they're connecting the payload fairing with JUNO inside to a crane. It's going to lift it up and place it down onto the truck. This is a special truck called a KMAG, which we use to transport the payload fairing containing JUNO out to the launch pad. This is still at Astrotech. You can see they're getting ready to disconnect the crane and move the whole truck and JUNO out off to the launch pad. So here it comes. We left the Astrotech facility around 2 a.m. We had crews that preceded this transport convoy to make sure the roads were clear. Here you see the KMAG slowly moving out of the building at Astrotech. The KMAG did reach a top speed of about 10 miles per hour, so it took 3 or 4 hours for the whole convoy with the payload fairing to make it from the Astrotech facility out to the vertical integration facility at Slick 41. So we went off into the night. The roads were cleared. We had appropriate convoys. We got the spacecraft and inside the fairing safely conveyed out to the launch pad.
Well, Jen, let's go to the other side of this now. After we've come off the rocket, which I gather is like 57, 58 minutes after launch. Tell us what's going to happen in the first 5 minutes, the first 10 minutes, the first couple of hours.
Well, the first things that we're going to do is establish communication with our ground station in Canberra. We will be looking to confirm that link within the first 5 minutes or so after we separate from the Centaur upper stage. The Centaur will leave us at a spin rate of about 1.4 RPM. 5 minutes after separation, we will fire the first pair of solar array SEP nuts to deploy the arrays, and we do that at 5 minutes. We do the next pair at 6 minutes. That releases the arrays. The arrays will deploy in a couple minutes. As they deploy, it's like an ice skater extending her arms, and we will spin down to about 0.4 RPM. Then we will use our own thrusters to spin us back up to our 1 RPM cruise spin rate. The launch vehicle should leave us oriented within about 20 degrees of sun, so that we should be able to get sunlight on the solar cells immediately and start recharging our batteries. If it does not, we have the capability to detect that and then precess the spacecraft so that the arrays will be pointing at the sun and being able to recharge the batteries. Once we have those solar arrays deployed and sun on the arrays, we're in a power stable and spin stabilized condition. And so that's the moment I'm looking forward to.
Well, Jan, thank you very much. And we'll be looking forward as much to spacecraft separation as I'm sure the Atlas team will be looking forward to liftoff. So thank you very much for coming over and talking with us.
Thanks very much, George. Looking forward to a great day.
And we're at T-minus 1 hour, 47 minutes, 52 seconds and counting. This is Atlas Launch Control.
Centaur LO2 transfer line showdown complete.
Roger. Start Centaur LO2 tanking.
Roger.
Step 4.127, payload and CM ECS have been on GN2 for 40 minutes minimum.
Roger.
This is Atlas Launch Control, T-minus 1 hour, 45 minutes and 43 seconds away from our launch today. Actually, we have one remaining planned 10-minute built-in hold, which brings us about 1 hour, 55 minutes and 30 seconds away from the actual liftoff. And joining us now here in the Atlas Spaceflight Operations Center is John Calvert. He is the mission manager from the NASA Launch Services program at Kennedy, and he has been very much involved with the Atlas V and the interface between the Atlas V and the JUNO spacecraft and all of the associated activities to get an integrated launch vehicle and JUNO spacecraft ready for a launch today. So, John, we have a tape of some of this activity with the Atlas V, and I wonder if you could tell us, we're going to roll the tape now, tell us what it is that we're seeing.
Sure, absolutely. Thank you, George. Okay, starting on this tape, you see we have our Antonov aircraft that is actually used to transport the Atlas V booster and Centaur to the launch site. And here it is out on the Cape Canaveral Air Force Station skid strip. You can see it kind of in a kneels down configuration. It kind of actually kneels down there in the front, enables easier offload of the booster, which they align those tracks and slowly winch it and pull it out of the front of the Antonov aircraft, where it's loaded onto this transportation dolly. And the goal of this phase is to get the booster from the airstrip over into the building we call the ASOC. It's actually the building we're in right now today, George. It's the Atlas Spaceflight Operations Center. So they bring this down. This occurred about late May. Was transported down to the Cape Canaveral Air Force Station. The first flight of the Antonov brought that down here, where now that these guys are moving this over into the ASOC, the Antonov is now turning around, heading back to Decatur to pick up the Centaur, which a couple of days later has landed. And now they're offloading the Centaur, the upper stage of the Atlas V rocket, and doing a similar type transportation operation to move it from the Antonov and deliver it over to the ASOC, where it's stored for a little while to do a kind of a receiving and inspection, but nothing more than that. It's waiting for its chance to get moved out and integrated in the vertical integration facility for stacking operations. So you can see those are very tight corners. They have handlers going around the vehicle watching at all times, moving it real slow to make sure that they don't hit anything. And there's our booster is set there on the side, and the Centaur is being backed into position right next to it. Okay, so now in mid-June, they're ready to start the stacking operation out in the vertical integration facility, and here they begin the transportation operation to take the booster out to Complex 41 in the vertical integration facility. And this is another long day of work where they've got a lot of lift operations. They take the transport vehicle out there, get it aligned, and you can see they use both a mobile crane there and the facility crane that extends out and helps lift one end. So they've got a handling fixture on the back end. They then lift it up, get the transport vehicle out of the way, where I think a later shot will show this actually setting down on what's called a breakover fixture, which is positioned on the rails outside of the vertical integration facility, and allows that booster to be swung in and slowly lifted. There you can kind of see the breakout fixture on the bottom there, and that's on those rails, and those rails slowly push toward the vertical integration facility and allow that booster to be rotated into the vertical position. So it's lifted up, brought inside the facility, and lowered over the launch head of the mobile launch platform. You can see some of the taglines. So obviously we had good weather on this day, and weather operations and all these operations usually begin with a weather briefing and some sort of pre-crew briefing to make sure that all the weather is a go for the day. And now we've transitioned. Now we're showing the arrival of one of the solid rocket motors that will be utilized on JUNO. And as you're aware, JUNO is we call an Atlas 551 configuration. It actually has 5 of these solid rocket motors on board. This video will show you the offload and the loading operation of one of those motors. Again, these are solid rocket motors built by Aerojet, brought to the Cape, offloaded on the transportation trailer onto this erection trailer, where it's rotated to the vertical position. The facility crane can then lift this solid rocket motor up and bring it inside the facility. You can see workers watching closely. None of these operations happen quickly. Very good shot there of the erection trailer being raised, and here's the motor being lifted and taken inside the facility.
And you said there's 5 of these on this rocket, is that right?
JUNO requires all 5 of these solid rocket motors, which is the most that the Atlas can handle. You'll see MSL coming up as a 541 configuration, so they only require 4 solid rocket motors. But
will these all ignite at the same time on the ground, or
these will all ignite at the same time on the ground? And I think Vern will tell you a little bit about the flight operations he's coming up, but they'll jettison just a second apart from each other. But here it is again, taglines, operators watching, and you can see that all 3 or all 5 of the motors at this point have been installed. So that operation, it takes about 1 day to do a solid rocket motor. So the more motors you have, obviously that added about a week to the schedule with a 551 configuration. And now we've brought the Centaur upper stage out to the vertical facility to rotate it and lift it and mate that to the top of the stack. What wasn't shown there is in between the solid rocket motors and the Centaur, there was what they call a booster interstage and a Centaur interstage, which were also brought out, taken up, and installed on the vehicle. So the Centaur can set down on those. And here, at the end of the video, we see the operations. I think Jan told you a lot about what went on out at Astrotech and the encapsulation process. And here, on about a week and a half ago, we rolled out the encapsulated JUNO spacecraft, and it's being taken out to Complex 41 and lifted, and this will complete our stack of the entire JUNO launch vehicle. And this occurred Wednesday of last week, so not that long ago. You can see they do some final checkouts, a final integrated systems test after this to make sure everything is checked out and working. And that brings us to where we are today.
Well, the interface between the spacecraft and the rocket, is that pretty much standard for every mission, or is there something that's customized between the spacecraft and the rocket? Is it different, or is it?
Everyone is different. ULA does have a catalog of pretty standard interface and payload separation systems that they use, but those can all be different and modified. In the case of JUNO, we had an actual extra adapter space, adapter put into the stack to allow clearances of the solar array, solar arrays inside the fairing. So actually my involvement with JUNO goes back to really the concept phase. I was involved. I'm proud to say I was involved from when it was a concept. It was highly competed back in NASA's announcement of opportunity process. So I've been involved from JUNO from the start in evaluating, their launch vehicle needs and hopefully getting them, helping them get to where they are today.
So seeing that spacecraft separation from the Atlas will be a high point for you today.
That's what we're all waiting for. We're looking for a good separation, making sure we put them on the right trajectory, and watching those or learning that those solar arrays have deployed successfully.
Well, John, thank you very much, and we'll be looking forward to that as well. And thanks for telling us the story about how the Atlas got to where it is today.
My pleasure, George. Thank you.
And we're at T-minus 1 hour, 37 minutes, 10 seconds, and counting. We have about 15% of the liquid oxygen on board the Centaur right now. This is Atlas Launch Control.
Centaur bottles at flight mass.
Roger, bottles at flight mass.
It's 4.139.
I copy. Thank you.
Centaur LO2 at 40%.
Roger.
T-minus 1 hour, 33 minutes.
Pressurize Centaur LH2 storage tank to chill down level.
Roger. Centaur LO2 at 50%.
Roger. All sequences through 4.125 are complete.
CFA purge has been in displacement mode for over 25 minutes.
Roger.
This is Atlas Launch Control, T-minus 1 hour, 30 minutes and counting. Joining us now here in the Atlas Spaceflight Operations Center is Vern Thorpe. He is the program manager from United Launch Alliance for NASA missions. And Vern is going to talk us through some of the flight events of the Atlas as it lifts off and flies out on its mission. First of all, Vern, we touched on it a little bit in our last interview with John Calvert. There are 5 solids on this one, but the Mars mission's only got 4, and how does all of that get determined?
That's correct, George. That's correct, George. We have 5 solid rocket boosters on the Atlas that we're launching today. That's the maximum number we can have. We can fly with anywhere from 0 to 5. And for the JUNO mission, because of the weight of the spacecraft, it's a fairly heavy spacecraft for an interplanetary mission, weighs about 8,000 pounds. And because of the energy that we need to give to it to get it onto its interplanetary trajectory, we and our partners at NASA decided to use the most powerful configuration of Atlas that we have. We actually used the same configuration for the Pluto mission about 5.5 years ago. We launched that one in January of 2006. So this will be the second time that we've had a mission that required 5 solid rocket boosters, and it'll be actually the 27th time that we've flown Atlas V overall. With those 5 solid rocket boosters, each one of them puts out a little more than 300,000 pounds of thrust each. So when you add those together with the core that puts out about 900,000 pounds of thrust, we'll be lifting off today with 2.5 million pounds of thrust.
And do all of those 5 solids light off at the same time, or is that staggered?
Yes, no, we light them all at the same time on the ground. We'll light the core engine first, and we monitor it for a very brief period of time to make sure it's coming up to speed properly. And as soon as those health checks are complete, we'll light all 5 solids simultaneously. And when that happens, you know you're going somewhere.
Okay, we'll go ahead and roll the tape now. And Vern, if you can tell us about the flight profile that we'll see the Atlas fly today.
Sure. As I mentioned, we'll start off with about 2.5 million pounds of thrust on the ground. This is actually real footage from the Pluto mission that we flew a few years ago for NASA. After liftoff, the first major event you'll see in the flight sequence is the burnout and jettison of those 5 solid rocket boosters. And we jettison them in 2 groups, like you see right there. That's about 1.5 minutes into flight. 3.5 minutes into flight, we'll be at an altitude of 63 nautical miles, pretty much out of the atmosphere, and we'll jettison the payload fairing. And then 1 minute after that, about 4.5 minutes into flight, we'll have used up all the fuel in that Atlas booster, so we'll shut down the engines. We'll separate from the Centaur upper stage, and then we'll back the booster stage away. It'll splash down and sink in the ocean. At that time, we'll light the Centaur engine for the first of 2 burns. That first burn will last about 6 minutes, and it will put us into a low Earth parking orbit. That parking orbit will have us coasting for about 33 minutes, a little over half an hour. At that point, we'll be over the southern Indian Ocean. We'll light the engine for the second and final burn of Centaur, and that burn will last about 9 minutes. It will end over Australia. And at that point, we will have placed JUNO into an interplanetary trajectory. Once we've done that, we'll orient to the separation attitude that the spacecraft needs. We'll initiate the separation sequence. And then as the spacecraft begins its mission, we'll do a series of maneuvers with the Centaur upper stage to get it out of the same orbit and make sure there's no chance of recontact or contamination.
And then what happens to the Centaur?
Well, we're putting JUNO into an orbit that initially will take it out past the orbit of Mars into the asteroid belt, where they'll do some maneuvers in preparation for an Earth flyby in a couple of years. Centaur will be in a similar orbit. We'll change the orbit enough so that it'll not recontact or be in the vicinity of JUNO, but Centaur will go into an orbit around the Sun, and we did a few checks, some analyses between us and NASA to make sure it wouldn't cause a problem in the future, and it'll just orbit out there indefinitely. We'll probably never see it again.
Well, we've got a number of other launches with United Launch Alliance this year. Could you kind of run down the order a little bit in chronological sequence, what's upcoming for us?
Sure. This is actually the second of 5 launches that ULA is doing for NASA this year. The first one, of course, was Aquarius that we launched on June 10th of this year. That was on a Delta II. JUNO obviously is flying on an Atlas V. Next up is the Grail mission that flies about a month from now. I believe the launch date is September 8th. That will also fly on a Delta II from here on the East Coast. Next up after that is another Delta II, the NPP mission, which is an advanced weather satellite. We'll fly that one out of Vandenberg on October 25th, I think. And finally, we'll end the year with NASA with a launch the day after Thanksgiving of the Mars Science Lab, which will be the biggest rover that NASA has ever placed onto the surface of Mars. That will use an Atlas V, and it'll be similar to this. It will have one less solid rocket booster. It doesn't need quite as much energy, so it will fly on an Atlas V 541, the 4 meaning that we have 4 SRBs.
Well, thanks, Vern, and we'll be looking forward to actually seeing this actual flight profile here in just a few minutes actually occur as it's been outlined for us here. So thanks very much for coming by and talking to us.
Okay, thank you, George. My pleasure.
And we're at T-minus 1 hour, 24 minutes and counting. This is Atlas Launch Control.
Centaur LO2 at 95%. Topping started.
Roger.
Atlas LO2 airborne chill down and slow complete. Fast fill started.
Roger.
T-minus 1 hour, 20 minutes.
AHBs at flight pressure.
Roger. All sequences through 4.131 are complete.
This is Atlas Launch Control, T-minus 1 hour, 18 minutes, 22 seconds, and counting. That means we're about an hour and 28 minutes from launch. We have one remaining 10-minute built-in hold coming up. Joining us now in the Atlas Space Flight Operations Center is Scott Bolton. Scott Bolton is the principal investigator for the JUNO mission from the Southwest Research Institute. And Scott is what we call the principal investigator for a PI-led mission, which is a little different in the context of some others that we do. And I wanted to start by asking Scott, what exactly does a PI-led mission mean?
So a PI-led mission is different than some of the other missions because it's led actually by the PI team. Other missions that are directed by NASA are led by NASA centers. So what that means is that an announcement of opportunity comes out. I put together a team that includes the engineering, the management, the launch, the science, the outreach, everything associated with that whole mission. We put in a proposal together, and when NASA selects that proposal to get developed and eventually launch, they put me in charge. So what I'm basically responsible for everything associated with the mission. And they term that principal investigators. Then I have a number of scientists on my team, and they're called co-investigators. Normally, the term principal investigator refers to a scientist that's in charge of an instrument on flagship type missions. In this case, a PI-led mission means the principal investigator is responsible for the entire mission.
So are these a combination of both Southwest Research Institute teams or JPL or some combination? Who all comprises your science team?
So the science team is spread around the whole country. It has some people from Southwest Research Institute, some people from JPL, different universities, NASA systems, even people internationally. The team, when I say that I put together a team, I put together the whole engineering team as well. So we have the spacecraft team from Lockheed Martin. I have a management and navigation team coming from Jet Propulsion Laboratory. They also will do some of the operations. So I delegate each of these different teams different things to do. In the case of JPL, they're delegated the day-to-day management. They also get the navigation, some of the operations. Lockheed builds the spacecraft. They also do some of the operations of the spacecraft. And the instrument teams they've been delegated, of course, to build their instruments and operate them as well.
Now, we've got some international participation on the mission. Can you mention who some of the more significant international partners are in JUNO?
Absolutely. The most significant contributor is the Italian Space Agency, ASI. And they contributed 2 instruments, the JURAM instrument, which is an infrared mapping spectrometer, as well as the KAT, which is a piece of our gravity system, which measures Doppler signals from the spacecraft. Other international contributors are Belgium, which helped us with the ultraviolet instrument, France, which helped us with the plasma instrument. We also have Denmark is doing part of our cameras for the magnetometer. And then we have a number of co-investigators from other countries, such as the United Kingdom as well as France.
Well, Scott, we've got some animation now of some of what Juno will be doing at the planet. And if we could go ahead and roll that tape, and Scott, tell us what it is that's happening.
So here you see the Juno spacecraft. It's cartwheeling through space. That's how our normal operations will be. We rotate twice per minute. You see the giant solar arrays there sticking out. Each one is about 8.5 meters long. In this animation, you're starting to leave Earth, headed toward Jupiter. Now, on the end of one of those solar arrays, you'll see kind of a funny object, which is the magnetometer boom. The other two solar arrays are identical. That one is a little bit different because it has this magnetometer boom. On the end of that are two cameras, and there are two magnetometers and 4 cameras to help locate that boom and measure the magnetic field very precisely. In the middle of that was the high gain antenna. On this animation, you're seeing one of the primary goals of Juno, which is the origin of Jupiter and the origin of our solar system. Here you see the very early solar system, the cloud or nebula of gas that it formed our star, our sun. And then as after the sun forms, you see a disk of material or debris left over. Most of those leftovers go into Jupiter. Of course, the remaining leftovers create the rest of the solar system. And you see one artist's conception of how that might have happened with this rotating angular momentum, spinning around and collapsing down into different disks. Juno's is set up to learn about that early part of the solar system and learn how Jupiter formed by measuring the ingredients. We're really looking for the recipe for planet formation, and we're going after the ingredients of Jupiter by getting the water abundance, as well as the very precise measurements of the gravity field that will help us understand whether there's a core of heavy elements or a core of rocks in the middle of Jupiter. These two kinds of measurements help us discriminate among theories of how the early solar system was and how Jupiter formed. And there you see Jupiter forming, probably the first planet to form. It's so big, almost all the rest of the solar system could fit inside of Jupiter, other than the sun itself. And so it really did get the bulk of the leftovers. So if you want to learn about the Earth and the early solar system, you have to go back to Jupiter. This animation is showing you models of the interior. So you saw the beautiful clouds, the things that we normally see, and it's unwrapping, sort of peeling the onion or looking at different layers of Jupiter all the way down. The first part was the metallic hydrogen, and as we go down in pressure, it starts to get squeezed and squeezed. The dark part might be metallic hydrogen, and the question is whether there's a core in the middle of that. If there is a core in the middle of Jupiter, what it means is that solids probably formed in the early solar system before Jupiter did. So that tells us when Jupiter formed. This animation is about the Doppler signal. And so what you see is the spacecraft comes down very close to Jupiter and it gets pulled and tugged. And what we're looking for is departures from its velocity or its trajectory from our model, which would be all the mass of Jupiter is one point in the center. And it's because the mass is distributed differently, the spacecraft moves around a little bit differently. We make these Doppler measurements and watch that, and we're able to figure out how the mass is distributed. This is the magnetic field of Jupiter. You see the beautiful aurora in the north and the south. These magnetic fields are an invisible force field going out and coming all the way around the planet, much like the Earth's. Jupiter, of course, is the most powerful magnetic field in the entire solar system other than the sun. And so it's got the most powerful planetary aurora.
Well, Scott, Juno, after we launch it today, it's got to come back. Can you tell us a little bit about the orbital mechanics involved in all of this?
So what we do is we launch out on the rocket, but of course once you leave Earth, you're still trapped by the sun. You're just going around the sun just like one of the planets is. And we're in an ellipse. And if we had more energy, we could make that ellipse big enough to reach Jupiter. But what we do is we use one of the most powerful rockets that exist, and we go out, and we go all the way around, and when we come back 2 years later, we time it so Earth is right there, and we fly by Earth very close, and Earth actually accelerates us. increases our velocity, much the same as if we had another engine on the rocket. And that allows us to have a bigger ellipse going around the sun and eventually reach all the way out to Jupiter. So we spend 2 years in the inner solar system, come back, use the Earth as a gravity boost, and then 3 more years we reach Jupiter.
The spacecraft, it's about a 5-year cruise. Is that right out to Jupiter?
5 years, 2 years around the sun for the Earth, and 3 more years out to Jupiter.
Does it do any science between here and there, or is it kind of quiescent until you get to Jupiter?
It's mostly quiet, although we will do calibrations, and the instruments have to be, run every so often just to keep them operating and get them checked. There will be some science opportunities. We haven't mapped all those out. One of the big ones is just flying by the Earth with Juno's set of instruments. We can learn some things about the Earth, and we can also learn about our spacecraft and how it operates by operating at Earth. So we have a plan to do that when we come by the Earth 2 years from now. And then we'll do some more science, monitoring probably the solar wind. If we see that we're going close by any asteroids, we'll certainly try to get some new science with those on the way out to Jupiter.
Well, Scott, thank you very much. And we're certainly looking forward to the initial phase of the flight today. And you're looking 5 years from now. That will certainly be the crescendo of the last, I guess you've been working in this about three years?
Oh, no, longer than
that.
Probably closer to 11 or 12 years. It's been a long time. One of the things in this business, you got to learn patience.
So I guess from the catalyst of the concept, it takes that much time to actually start building the satellite, building the spacecraft.
Absolutely. There's a lot of advanced technology in this, and it takes a lot of time to build it.
And one final question. This we're using solar arrays here. Does that mean that the JUNO spacecraft is inherently relatively low power to be able to use these kinds of arrays, or what's behind that secret?
That's true. We are relatively low power. We're very efficient. Out at Jupiter, we're about 400 or 500 watts is what we use. About half of that is to run the spacecraft and keep it warm, and the other half is to run the instruments. But we're naturally efficient, even with these giant solar arrays, and they are quite big.
Well, Scott, thanks very much, and we'll be looking forward to spacecraft separation, and you'll be on your way. Thank you very much.
Thank you very much.
And we're at T-minus 1 hour, 7 minutes, 30 seconds, and counting. This is Atlas Launch Control.
Atlas LO2 at 40%.
Roger.
T-minus 1 hour, 5 minutes.
Start CFA purge to control mode.
Roger.
This is Atlas Launch Control, T-minus 1 hour, 4 minutes, and 56 seconds and counting. The Launch Services Program, headquartered at Kennedy Space Center, is in charge of the launch management for NASA today during the countdown, and their involvement begins fairly early in the process when we first begin to take a spacecraft that we know is going to need a launch and pair it with a launch vehicle, and then do all of the things that are necessary to work with the United Launch Alliance to get that rocket ready to fly, as well as working with the spacecraft itself. So we'll look now at a little bit about how that works with Earth's Bridge to Space.
Team's ready.
Okay, 5, 4, 3, 2, 1. Liftoff. And Pegasus is away.
Over 200,000 feet. Vehicle's recovering very nicely from the liftoff transient. We're looking real good. We're now past Mark 1. The vehicle is now traveling faster than the speed of sound.
The Launch Services Program is based at NASA's Kennedy Space Center in Florida, but its reach is felt throughout the United States and research labs all over the world. The Launch Services Program has given life to some of our nation's greatest space achievements. The Mars rovers, Stardust, Genesis, and New Horizons are just a few of their recent missions. Charged with selecting launch vehicles for NASA's science and exploration missions, LSP works with industry partners to define requirements and determine the best launch vehicle for each mission. Expendable launch vehicles are part of a balanced and diversified launch capability for NASA. Logging more than 50 launches to date and amassing an impressive record of success, LSP provides an invaluable service to NASA's science and exploration community. As the primary liaison between the spacecraft and the launch vehicle, LSP is the critical step in making a mission a reality. Once the spacecraft and launch vehicle are complete, LSP coordinates the timely rendezvous of rocket and spacecraft at the launch site. The launch site is the place where the mission really comes together. The spacecraft is mounted to the assembled rocket, and final testing and checkouts are conducted. If all systems are go, the mission is declared ready to launch. Launching one mission to space is hard enough. Try juggling a manifest containing up to 30 missions at any given time. These achievements are a result of the dedicated professionals at NASA's Launch Services Program, a team guided by excellence and driven by a passion for space. Years of reviews, certifications, and hard work pay off with a roar of engines and a brilliant trail of fire and smoke.
Right now we have about 50% of the liquid oxygen on board the Atlas that we're going to need, And we're getting into our liquid hydrogen tanking operations for the Centaur stage. At T-minus 1 hour and counting, this is Atlas Launch Control.
Atlas LO2 at 60%.
Roger. Initiate BRC ECS.
Roger.
All steps through 4.139 are complete.
Centaur LH2 at 10%.
Roger.
T-minus 55 minutes.
Start flight control final preps.
Roger.
Centaur LH2 at 20%.
Roger.
Atlas LO2 at 70%.
Roger.
Centaur LH2 at 30%.
Roger.
Centaur LH2 at 40%.
Roger.
This is Atlas Launch Control, T-minus 50 minutes, 26 seconds and counting. We have one remaining 10-minute built-in hold at T-minus 4 minutes. And at this point, we are just about exactly 1 hour away from the launch of the JUNO spacecraft on the Atlas V. We're now at 50% liquid hydrogen on the Centaur stage. Among the mission logos and other insignias adhered to the side of Juno's Atlas V is a tribute to Rick Gramier of NASA's Jet Propulsion Laboratory. There is also a plaque on the spacecraft recognizing Rick. He was Juno's first project manager, and he played a critical role in getting Juno from concept to what we see today, a spacecraft a little more than an hour away from a voyage to discover Jupiter. The plaque reads, "In loving memory to our colleague and friend Richard S. Gramier, the Juno team." And for nearly 20 years, Jerry Perry was involved in the facility to support both the Atlas and the Titan launch programs, so this mission is also dedicated to him by United Launch Alliance. As the recognized man behind the scenes, Jerry was completely devoted to the launch industry and the concept of total mission success. Throughout his career, Jerry received many commendations and exceptional achievement awards and treated each and everyone with dignity and respect. Jerry's word was as good as gold, and he'll be truly missed by his United Launch Alliance family. And we're now at 60% on our liquid hydrogen levels going into the Centaur stage. At T-minus 48 minutes, 30 seconds, and counting, this is Atlas Launch Control.
Centaur LH2 at 70%.
Roger.
Centaur LH2 at 80%.
Roger.
Centaur LH2 at 90%.
Roger.
Atlas LO2 at 90%.
Roger.
T-minus 43 minutes.
Centaur LH2 at 97%. Topping started.
Roger. Perform Centaur LH2 fill and drain valve cycle test.
Roger.
Perform Centaur LO2 fill and drain valve cycle test.
Roger.
T-minus 42 minutes.
Centaur LH2 fill and drain valve cycle test complete.
Roger.
Centaur LO2 fill and drain valve cycle test complete.
Roger. Perform Centaur SRV and LH2 SVV cycling test.
Roger.
ECB at flight pressure.
Roger.
T-minus 40 minutes.
Start final open loop FTS test.
Roger.
Atlas LO2 at 97.5%. Topping started.
Roger.
Centaur SRV and LH2 SVV cycle tests complete.
Roger. Resume Centaur LH2 topping to flight level.
Roger.
Resume Centaur LO2 topping to flight level.
Roger.
Atlas LO2 at 99.6%.
Roger. Cycle Atlas LO2 fill and drain valve.
Roger.
Perform Atlas airborne locks vent valve functional test.
Roger. T-minus 35 minutes. T-minus 32 minutes. T-minus 31 minutes. T-minus 30 minutes.
Start CISA purge conditioning.
Roger.
Secure onboard video power.
Roger.